Hello. In this video, I'm going to solve this problem involving a wire which has been formed into a straight line plus a loop. I will assume that the wire is much longer than the loop. We're interested in finding the magnetic field at the center of the loop. Okay, so to solve this problem, I'm going to use the principle of superposition. That is, the magnetic field in the center of the loop. Center of the loop is the sum of the magnetic fields caused by the line, straight line of current and a loop of current. So I'm going to break those apart to those two parts, find their magnetic fields independently, then add them back together. Okay, so step one, I'm going to do the line. Okay, so I have a line of charge, or sorry, line of current, not charge. And I'm going to use the right-hand rule, put my thumb in the direction of the current, my fingers curl into the direction of the magnetic field, and I see that it is coming out of the page on this side and into the page on this side. So according to the picture up above, I'm interested in a magnetic field which is coming out of the page. Okay, now let's try to find the magnitude of that magnetic field. It is a distance, well, the radius of the circle is capital R. R is also the distance from the line to the center of the loop. Okay, so I'm going to try to find the magnetic field, a distance R from a line of current. Okay, so what I'm going to do that is I'm going to add up little DLs of current carrying wire and add up their effect on a point, which will be that point, that is a distance. So there's a distance R there, and a distance, we'll call that little r, the distance from my little DL, or a little DL. And this angle here, we shall call theta. Okay. So according to way magnetic fields work, we have B, magnetic field, is equal to the integral over all the little DLs. So integral from minus infinity to infinity of it's mu naught I over 4 pi r squared sine theta dl. Okay, now r squared is r squared plus x, or well, x, or I guess we're calling it in this case L squared. Okay, that's cool. We also have that the sine of theta is equal to r over the square root of, well, or over little r, which is the square root of r squared plus L squared. Putting that all together, I find that the magnetic field B, I'm going to write it without a vector sign here because I don't have a vector on the other side. So minus infinity to infinity of mu naught I over 4 pi r squared plus r, or plus L squared. And then r, which is our sine, which is r over square root of r squared plus L squared dl. Simplify that. B is equal to, we can bring all the constants out front, mu naught I r over 4 pi, the integral from minus infinity to infinity of 1 over r squared plus L squared to the 3/2 dl. You can do this integral. I'm just going to look up the integral. So if you look it up, you'll find that that is equal to not I r 4 pi and it comes out to be L over R squared, the square root of R squared plus L squared to the evaluated at minus infinity and infinity. And that's evaluated L is equal to minus infinity and infinity. Plugging those numbers in, I get B is equal to, okay, well, if I plug in infinity, for an L here that dominates this R, so I can just throw this R away, you get square root of L squared, which is just L that cancels the L on the top, and I just get a result of 1 over R squared. For the minus infinity, I get the same thing, except for there's a minus sign at the top. You add them together, you get a factor of 2, and I get mu naught I R over 4 pi 2 over R squared, because there's still that R squared there. Okay, in other words, B is equal to mu naught I over 2 pi R. So that is the magnetic field due, we'll color this in green, that is the magnetic field due to the line. I still have to do the magnetic field due to the circle. Okay, so the circle is a whole lot easier. The circle is easier because if you draw a circle like this, and suppose we have a little segment DL here, and we have a center there, the angle there happens to be 90 degrees. It's a rule about circles, that the radius is perpendicular to the circumference. Also, all of the points, all the little DLs around the circle are all the same distance from the center, the definition of a circle. So we can write the magnetic field of the circle as it'll be mu naught I times the length. So the length around is 2 pi R. That's the total length of the circle, over 4 pi. And then the distance is always R, so it's R squared, sine of 90 degrees, which happens to be 1. And that's that. So we can simplify that. We get B is equal to, so the 2 pi cancels with this, makes that a 2. One of the R's cancels, sine is 1. I get mu naught I over 2R. So that is the magnetic field due to the circle. Now, by superposition, to get the total magnetic field of the circle plus line, I can simply add them together, and I get B is equal to, okay, so they both have, you look in here, like here, they both have a mu naught I over 2R. It's just this one has a 1 over pi, this one doesn't. So I can write this as mu naught I over 2R 1 plus 1 over pi. Interestingly enough, the infinite line charge contributes only a 1 over pi, less than a third as much as the circle. So that's how you find the magnetic field. And I should specify the direction. So I'll give it a vector and say out of the page, because both fields are out of the page, right? If you do the circle, it's use your right hand rule. The circle says that the magnetic field is out of the page on the inside and into the page on the outside. The line is also out of the page. The magnetic field of the line charge is also out of the page. So they just add together like that, and they're both out of the page. So we can say this is our final answer. And that completes the solution to that problem.